Next, we're going to study wave actions. We have 4 wave actions: reflection, refraction, diffraction, and interference. The first one we have here is reflection. Well, reflection is the bouncing back of a wave when it hits a barrier. So you jump into the pool, water waves go and they hit the side of the pool and they bounce back. Well, that's a reflected water wave. Wake up in the morning, you look in the mirror, you see your reflection. What you're actually seeing is light bouncing into the mirror, bouncing back into your eye. Once again, wave reflection. If you've ever walked into a tunnel or an empty room, you may have heard your sound echo. That repeated sound wave over and over again, that is also wave reflection. We have a thing called the law of reflection, which says that the angle of incidence equals the angle of reflection. So this incoming angle equals the same angle that gets bounced off. So some examples of reflection, as I said before, are looking into a mirror, any type of a smooth surface you'll see reflection. When you come into the classroom, the lab tables are pretty smooth, and when the blinds are open, you can see a reflection of the high school in the lab tables that are along the window. And I've also mentioned an echo is a example of reflection. Now, there's a thing called echolocation, and that is what some animals use to locate objects. They send out a high-frequency sound, high-pitched sound that they then receive after it's bounced off of something else, and they can identify where things are based on how long it takes for that sound wave to come back. So our second wave action is refraction. This is when a wave changes its speed and direction as it enters into a new medium. So over here on the right, we have a picture of a pencil that appears broken as it enters into the water. But you pull the pencil back out again, and the pencil really isn't broken. So what you're seeing here is the fact that the light that's coming through the water into your eye is coming at a little bit different of a speed. So it's changing the location of where you think the pencil is. The pencil still is there, but just it perceives to be a different location. Same thing if you ever have to scoop anything out of the deep end of the pool and you use the skimmer to get it out. You have to kind of move a little bit more left or right than you actually where you think it is, because the light waves are being refracted. Shining white light through a prism is another example of refraction. So visible light or white light, what we see are all the colors of the rainbow: red, orange, yellow, green, blue, indigo, and violet. The color that we see will depend upon the wavelength of that particular color. So red having the longest wavelength and then the violet having the shortest. So what's shining into the prism is white light, which is a combination of all different colors of light. As the white light shines into the glass prism, because of their different wavelengths, they travel at different speed through the glass prism. When they travel at a different speed, it's kind of like a car when it goes through a puddle. It goes into a new medium, it starts to slow down, changes its speed. And sometimes cars will swerve either left or right because of this new change into a different medium. So that's what's happening here. Because of the different speed, they're changing their direction. So when they come out the other side of the prism, you actually see the individual colors that make up white light. Those individual colors being red, orange, yellow, green, blue, indigo, and violet. Same way as how we get a rainbow. So we have white light shining through water droplets. The water droplets refract the light, and we see a rainbow in the sky. So some differences in refraction for light and sound. So first thing, looking into the water, this would be a reed that's sticking out of water. Anything that's looking into water, looking at a fish, looking at a reed, and the object is not exactly where it normally is. It appears broken, it appears larger, it's changed its shape or size a little bit because the light waves themselves have actually gone in a different direction. And then for sound, I mean, you probably have been in a pool underwater and you've heard someone call your name and it kind of sounds like your name, but that's because the sound waves have gotten a little changed as they went from the water into your ear. Also, you hear sounds when the windows are closed. Maybe you hear some fireworks going off, but your windows are closed. You can still hear it through the door. Sometimes people also put a glass up to the door. This helps you to hear what's going on the other side. That's also sound refraction. I really like this image of the marbles inside of the box. Now what's so neat about this is that these marbles are clear and this box has different colored checkered walls. And as you can see on the back of, or at the bottom, let's say down here, there are red checkers. Now they've changed their shape as they come through the marble. So what's happening is the light waves come up and instead of traveling in a straight line, they bend a little bit and come out. You can also see in this marble here in the center that there's some green here on the right side. That green came from this side wall. That's on the left. And then on the left side of that marble, you can see some blue. That came from the blue wall that's on the right. So those light waves actually traveled through the marble and came out the other end. Same thing with the marble here on the bottom. You can actually see the purple wall. See a little snippet of it down here, but the purple light went through the marble and came out the other end. So this is an example of light refraction. It's changing the speed and direction of the light. So here are two examples. So we have what's called internal reflection and refraction. So the red light beam is bouncing off the inside of this makeshift prism, and then it eventually comes back out again. So at these 2 points right here, we have some internal reflection where it's bouncing off the barrier and then continues on. The yellow and blue, however, you can actually see how the light changes its direction as it travels through the prism. That's what we call refraction. Same thing with the blue one, although a little more difficult to see. So here we have another example of wave refraction. You can see the high intensity beam of light coming in, and as soon as it hits the water, it starts to change its speed and it changes its direction. The rays of light appears a little bit broken. Now there's also something neat right here. Here's a little bit of light that ended up getting reflected. It bounced off the surface of the water. So here we have our third wave action, which is diffraction. Diffraction is the bending of a wave around a barrier. So there's a little opening right here, which I want you to think of like a doorway. So this would be a sound wave coming in, and then it goes through the doorway, and it bends around and fills up the entire space of the room on the other side of the door. So this is very similar to sitting in the classroom and having the door open to the classroom, and then you're hearing the sounds in the hallway without actually seeing the people. You know, it's also like, how do your dog and cat hear you? Well, sound waves diffract around all the barriers. Then wherever your dog or cat are hiding, I'm sure they hear their food being poured into their dish and then they come running. So I like to think of diffraction as the waves looking for a different way to go. So now for the differences between light and sound when it comes to diffraction. So really light does not diffract that much at all. This is why we have shadows. If you hold your hand up, you can actually make little shadow animals, which I know people love to do. And then I gave you an example of sound just before where you can hear the sound and you don't see the source. Just like your dog and cat can hear their food being poured and they come running. This is a picture of a lagoon. So a lagoon has this land mass on either side and a small opening for the water waves to come in. The water waves then come in and they fill in the entire empty space. So once again, the waves are looking for a different way to go. They go around the barrier. So our fourth wave action is interference, and this is when two waves come in contact with one another. And usually the result is going to be a change in the amplitude, how high or low the wave is going to be. So if you think about sports interference, it's when usually two players come in contact with one another. Very same thing here. Two waves are coming in contact. We're either going to get a larger wave as a result or a smaller wave as a result. We have two types of interference, constructive interference and destructive interference. So constructive interference, I have a new wave produced with a larger amplitude. The way this happens is two crests of two different waves meet at the same point, and two troughs meet. They build upon one another, and they make a wave with a larger amplitude. So the two crests and the two troughs have to line up for this to happen. So think about a construction company. Construction companies build things. They build houses, they build buildings. So constructive interference is building a bigger wave. Conversely, we have destructive interference. And in this case, we have a wave being produced with a smaller amplitude. In this instance, a crest and a trough will meet. Sometimes the resulting wave will be a smaller wave. In this case here, we have no wave left whatsoever. So these two waves canceled each other out. If this were two competing sounds, if I had one sound on one side and one on the other, you would actually hear absolutely nothing where these two sounds would interfere.